In this video, we're going to draw a structure for carbon dioxide. And one of the things we're going to see is that sometimes you can have more than one bond between two atoms, creating a double or triple bond. So let's see how this works with CO2. First off, we need to take into account how many valence electrons each element has. So we got carbon and oxygen. We have, and we want to have. Now both carbon and oxygen have to follow the octet rule, so they're going to want to have 8. If we go over to the periodic table here for a second, we can see that carbon sits right here, column 14, or 4A, meaning it has 4 valence electrons, and oxygen falls in column 16, or 6A, meaning it has 6 valence electrons. So when we fill this out, we're going to have, let's see here, what did I do? There we go. I'm going to have 6 valence for oxygen, 4 valence for carbon, and I need to multiply in or factor in the second oxygen. So at the end of the day, we would like to have 24 electrons. Reality is we have 16. To figure out how many bonds, we take 24, subtract 16 from it. We find we get 8. And remember, it takes 2 electrons to equal 1 bond. So we're going to have, divide that by 2, we're going to need 4 bonds. All right, so we've got 16 electrons. 8 of those electrons are tied up in bonds. So let's see what we can do. Well, first we have to determine the central atom. Remember, the central atom is always the least electronegative element, so that would be carbon. So down here I'm going to draw carbon. And I have to attach at least 1 bond to each oxygen. Then we have to make a decision. Do we want to put the 2 remaining bonds on 1 oxygen, or do we want to draw a Lewis structure where the bonds are split evenly between the 2 atoms? Well, let's take a look at both. First off, on the case on the left, we've got 3 bonds sitting right here. And that means we need to have 2 more electrons to complete our octet. So we're going to have 1 lone pair sitting on this oxygen. Likewise, the other oxygen is going to have a grand total of 6 electrons, or 3 lone pairs, sitting on its oxygen. And if we count our lone pairs and bonds, we find we have a grand total of 16 electrons used, which is exactly what we need for carbon dioxide. In the case on the right here, what we're going to do is we're going to fill in the remaining electrons on oxygen first, because again, it's the most electronegative. So 1, 2, 3, 4, and then the 2 bonds makes it 8. And likewise for the other side, 1, 2, 3, 4, 8 electrons there. So we've used all 16 electrons. We've got 2 Lewis structures, but only one of them is correct. Which one is correct? Well, we have to go to formal charge to answer that. So let's take a look. Right here on this oxygen, the formal charge is equal to the valence electrons, 6, minus the number of bonds, 3, plus the number of remaining electrons, 2, for a total of +1. So this oxygen has a +1 formal charge. And if we think about this, this is not an encouraging sign. Remember, oxygen's a highly electronegative element. It wants to have more electrons, not fewer. And so the fact that we've got an oxygen with a +1 charge begins to suggest this may not be the best structure. Let's take a look at the carbon next. Carbon has 4 valence electrons. We've got 4 bonds, no remaining electrons, so carbon is stuck at 0. So that's okay. And the final oxygen here, I'll draw my little arrow right there. Again, 6 valence electrons minus, in this case, 1 bond and 6 electrons for -1. So we've got 2 elements two oxygens, one with a +1 formal charge and one with a -1 formal charge. So if this is the best we can do, then this will be the correct structure. But let's see how the formal charge plays out on the other structure. So again, starting with carbon, we've got 6 valence electrons. We've got 2 bonds here. Both of them are in the double bond. We've got 4 electrons as lone pairs, giving us no formal charge on this oxygen. So this is a good sign. Well, this oxygen also happens to be the same structure as that oxygen. So we've got 2 oxygens with no formal charge. Again, going through carbon real quick, we've got 4 valence. It's got 4 bonds, no lone pairs, and no formal charge. So my structure over here on the right is the correct Lewis structure for carbon dioxide because it has the greatest number of atoms with no formal charge.